Okay, so welcome everybody. So today I'm very happy and pleased to introduce Karen. She got her PhD from Balseiro Institute and she was a postdoc at the Max Planck Institute. Nowadays, she's a professor at the Instituto Balseiro and a research director at the Bariloche Atomic Center. She has connections with our institute, being member of our International Advisory Council. She is the recipient of many awards and honors, such as the Guggenheim Fellowship and L'Oreal UNESCO Award. She works with condensed matter, and in particular, she worked in develop novel numerical methods to understand properties of quantum matter with applications in many systems and phenomena. So today, the title of her talk is Emergent Phenomena and Complexity in Quantum Condensed Matter. So please, Karen, thanks a lot for accepting our invitation, and please, when you are ready.
Okay, Tiago, thank you so much for your kind introduction, and hello everybody. As I was saying, hi to so many friends and known names, Peter Fulde, Gerardo Martinez, and everybody. I can't see everyone, Klaus Capelle, everyone. Hi, Peter. So, well, so nice to see you again. I'm sorry we have to see each other like this through a screen, but it's a great pleasure for me to be here again, at least virtually, at the International Institute for Physics. So thank you so much, Tiago and Alvaro and the people, Dimitri, who have invited me to give this seminar. I like to support this institute in every way I can, because I think it's one of our best institutes or physics centers in Latin America. So I think it's very important to sustain it, and even more in these times of the pandemic. So thank you once again. So now let me share screen, and I want to then start talking about the physics. I wanted to tell you what we're working on. So this is one of the main topics we're studying in Bariloche in our group, the condensed matter, theory of condensed matter group in Bariloche. Bariloche is in the Centro Atómico Bariloche. It depends on the National Atomic Energy Commission, and we have the Balseiro Institute, which is the university part where we train our students, and that depends on the University of Cuyo. So I wanted to talk to you today about what we're working on, as I said, which is emergent phenomena and complexity in quantum condensed matter. So before I start, I want to thank Bhaskaran for the paper you sent me yesterday. So very interesting. I'm glad to hear you're also working on this. Of course, we are of the school of Phil Anderson, so I think this is one of the very interesting main topics of condensed matter. So I try to convey the general message, and then what in particular what we are working on in this very vast and huge area of condensed matter physics. Just before I start, I want to show you where we are. For people who don't know, we're not so far. I mean, we're in Latin America, but in kilometers, we're many thousands of kilometers away from Natal. This is where we are in the south of Argentina, in Patagonia, close to the border with Chile, in a very beautiful place, which you can see here. I mean, this is a Tornador Mountain, and this is one of our many cold lakes in the national park. There's a ski resort, and it's a very pretty region to live in. And so you see in a straight line from Natal, we're quite far. But nevertheless, we are in spirit, we are close. This is the Bariloche Atomic Center, an aerial view. These are two other lakes, and this is the whole view from the campus. So here you see different houses where professors live and labs, and we also have a small nuclear reactor. It's a research reactor, since we have a lot of research also in nuclear energy and the peaceful applications of nuclear energy, of course. Our group is the condensed matter theory group, as I said, and it has also a theory, but we also have a very large experimental facility for condensed matter at Atomic Center in Bariloche. Let's go in now into the physics. What the concept of emergence here, to introduce you to this topic, I chose three different definitions. One is of the U.S. National Academies, and it states, let me read, that emergent phenomena in condensed matter and material physics are those phenomena that cannot be understood with models that treat the motions of the individual particles within the material independently. Instead, it says, the essence of emergent phenomena lies in the complex interactions between many particles that result in the diverse behavior and often unpredictable collective motion of many particles. So it has to do with strong interactions or interactions between the individual particles or basic entities we're trying to explain, and unpredictable behavior. So this is the emergent phenomenon. What does Phil Anderson say in More is Different, an article in Science, and also in his very interesting book? Phil's idea on emergence is about the reductionist hypothesis, which does not, he says, by any means imply a constructionist one. The ability to reduce everything to simple fundamental laws does not imply the ability to start from those fundamental laws and reconstruct the universe. So I agree with Phil. I mean, this is a philosophical attitude towards science and what can be done, but I think this is very practical and very fundamental also, that we do not need to resort to the basic, very basic description of the fundamental particles, for example, in physics, to explain what we see in condensed matter physics or in physics at different energy scales. Finally, Bob Laughlin, several years ago, also defined, he stated that everything that matters in science now is organizational. And so the reductionist or fundamental approach has stopped from being useful. This is also a very pragmatic point of view, and this is something I want to talk to you about basically in this talk. This is a long list of examples of consciousness, crystals, etc., superfluids, bosons and condensation, even the stock market. In the middle, we have the individual pieces, the individual entities which interact. Let's say the ant colonies are the ants, the consciousness are neurons, crystals and molecules. And to the right, we have, for example, the interactions among these individual entities, which bring finally the emergent phenomena in these systems. Like, for example, the interactions of the pheromone trails, or even neurons in consciousness, which bring neuron connections and firing. So this is a fundamental question, for example, what is the emergent phenomena of consciousness? So we don't even know what consciousness is, but there could be a question of how many, is there a critical number of neurons above which consciousness emerges, or maybe not even a critical number, but maybe a critical connectivity, or one has to define what the basic question is to define the emergent phenomena in consciousness, for example. Now going to something that I dominate a little bit better. So let's go to what happens in quantum condensed matter. Here, there's an interesting example. A paper that appeared in Science in 2012 by Bratzinski and collaborators. The main question they asked themselves is there a critical number of water molecules above which crystal order emerges? So they have a theoretical and experimental paper in which they go collecting different numbers of water molecules, H2O, and they form, they want to see when the crystal order emerges in this system. So they start, for example, here to the left, they have 123 water molecules. Then they add more, 293. You start seeing that there is an incipient crystalline order in this huge macromolecule. And then with 600 water molecules, you start seeing a basic structure, crystalline structure in this special ice solid. So The critical number is around 300, like it shows here, and this is an interesting question. When does the crystal order emerge in crystals, for example? Now, what if looking at the classical concept of emergence and quantum weirdness, or the quantum laws of physics, to be more precise. So the combination of both concepts is very interesting, and if we put them both together, then we get quantum condensed matter, which has, most of us know, very interesting behavior, and it's very complex to study as well. So let me give you some examples of emergence phenomena in these materials with strongly correlated electrons. So the basic physics behind this is the many-body physics, which is very complex to calculate. And some examples I've written down here in strongly correlated systems are, for example, emergent phenomena in Fermi liquids and non-Fermi liquids, mainly in low dimensions. So now I'll mention some. What is in red, I'll give you some examples about, and also behavior close to quantum critical points, for example. We also have examples of broken symmetry phases in certain crystals, like the liquid crystals, or phases with hidden order. We also have phases with topological order, like the fractionalization of charge, like in the fraction of quantum Hall effect, or the separation of charge and spin, or the separation between orbit and spin, the existence of magnetic monopoles, etc. So this is something I'll talk a little bit more about now in a little while. Of course, superconductivity, superfluidity, quantum coherent states is another emergent phenomenon, which is very interesting. Also critical phenomena, scale invariance, independently of the macroscopic composition. The behavior of cold atoms, the existence of, for example, metal-insulated transition, the Mott phase, and also, for example, the existence or the emergence of quasi-particles we use to explain phenomena in the scale of condensed matter physics. In the next minutes, I'll talk to you about the fractionalization of charge and spin, the phenomena of charge and spin separations I've been working quite a bit on. And this to show mainly to students what the idea behind charge and spin separation is. Let me show you this cartoon. In this cartoon, we have, for example, here we have a one-dimensional chain of spins. So you see in green, we have the sides and the spin up and down in this one-dimensional chain. If we hit this chain with a photon, we can extract an electron, and here we can form a hole. So now we have it in the second row, we have the same chamber with a hole, we have an excitation. Now, due to the interactions in the model, the spins can interact between themselves, and these spins or electrons can also hop to the empty side, or we can also say that the hole hops to the right, for example. So here you see the hole hopping to the right. And when the hole hops to the right, then you can see here we have a net spin excitation, because here we have two parallel spins, whereas the background has an antiferromagnetic distribution of spin. So this would be a spin half excitation. So we see that the spin half excitation can move towards the left, independently of the hole. So this is a cartoon of what we call the spin and charge separation. Well, this was very well studied by people like Haldane, Hans Schulz, Anderson, Lee Wu, etc. And then we also have a phenomenon called spin orbital separation, and this is a similar effect where one can move the spin independently of the orbital excitation of the system. This was also described in this paper, even measured in this paper in Nature by Schlapper and collaborators, where they have, for example, they measured it with X-rays in this one-dimensional system, strontium-2 copper oxygen, where this is this one-dimensional system, and they can very precisely show the separation between spin and orbital degrees of freedom, and the orbitals are the different orbitals of the copper. This is an interesting phenomenon, because the electron, like we know it, with its spin 1/2 and charge E, in a strongly correlated system, this entity, which we call an electron, in reality can split its main basic quantum numbers, and the spin and its charge can move independently. So this is a list of possible observations of this charge and spin separation, like in high TC superconductors, in these salts, Behcaz and Fabre, copper chains and ladders, carbon nanotubes, or one-dimensional cold Fermi gases, like I'll show. And the experiments that show, although not directly, but they're indirect measurements of charge and spin separations in 1D and 2D, are IV curves, which one can interpret with charge and spin separation, or RFS, angular resolve photon emission spectrum, and other experiments. And also, for example, in transmittance through iron ore bomb rings, and this is a calculation we also did several years ago. Just to mention, this is a nice experiment done in Ultracoats fermion gases. So it's several years ago in 2003, but in this group, they have a parabolic well, and they have around 1,000 lithium atoms. The lithium atom is a fermion, as the atom itself is a fermion, and then by using they have a one-dimensional arrangement of these lithium atoms, and then by applying special laser beams with different frequencies and with different polarizations, like it shows here on the left, they can excite independently spin excitations of this one-dimensional arrangement of fermions. They can excite spin, and they can also excite charge, but what they call charge here really is a density oscillation. So they can separate density oscillations from spin, and so then they can measure, for example, at the time zero, they have they can produce an excitation of the whole fermionic system, and then after a certain time, they calculated here that they could see. You see the dark gray and the light gray are the charge and the spin distributions in this system. So this is one nice realization of charge and spin separation in fermions. Let me take you back to 1993. So this is almost 20 years ago. We did a calculation while I was doing my PhD with my collaborators and my PhD director, Carlos Balseiro. What we did is a very simple calculation in a ring. So it's a one-dimensional system with periodic boundary conditions. And this is a Hallberg model. And we calculated spin and charge excitation separately as a function of the interaction. And we could clearly see the wave packets separating. So we could see the charge and the spin separating. So just to show you, for example, if the interactions are 0, U equals 0, this is a tight binding model in one dimension. So the x-axis goes to 16. We have only 16 sites. And at time t equals 0, we produce a wave packet with a net momentum towards the right, and this is the wave packet at t equals 0 you see here in the left. So as time evolves, we see the wave packet evolving. So the top and the bottom are two different densities. The top one is the charge density, and the bottom one is the spin density, calculated like this. So the charge density is the sum of the occupation numbers, and the spin is the subtraction of the spin occupation, up minus down. So as you see, for zero interactions, the wave packet moves to the right, and both spin and charge are completely one on top of the other. If U is very large, here it's 1,000 times the Hopin, time equals 0, we have the same wave packet, and then we see that, for example, the charge, which is the top curve, moves towards the right much faster than the bottom curve, which is a spin density. And you see here that there is like an exchange between them. They are not completely independent, charge and spin. We are not measuring the exact independent variables, but it gives you quite an idea of what's happening. And so you see the charge emerges through leaves the system to the right and appears again in the left, while the spin only moved only a couple of sites. The charge turned did a whole turn around the system. So this was fun to see, to explicitly see what happens in charge and spin separation in this toy model, let's say. Well, I brought this back because now recently, last year, or a year and a half ago, Google, you know, I mean that Google has this quantum computer called Sycamore. They built a quantum processor which is now beginning to produce results just in the very beginning of the simulation of systems of molecules, etc. So this was interesting to see the results. Before going to the results, I just want to mention something about this quantum computer, this superconducting processor. Well, in this paper published in October 2019, Google claimed they had the quantum supremacy. I mean, with this very sort of competing word, supremacy. And what they did is that they showed that with this lattice they have of superconducting processors, they could generate a real random number in about 200 seconds, while they claim that using a classical computer, this general quantum number would have taken 10,000 years approximately. Although, I mean, these results are now challenged by subsequent papers, but I mean, it's still very impressive. They had of the order of less than 50 qubits to perform this calculation. So it's not, I mean, the problems with error corrections and decoherence in quantum computers is still important. Very, very well. I mean, the applications in quantum computers for the future are really impressive because mainly in drug design and new materials design, or even to study climate finances, in optimization problems, of course, cryptography and communication. What did they do then? The collaborators in Google, I mean, it's published in arXiv, but I didn't see the published paper yet. So as far as I know, it's still on the arXiv. They did exactly the same simulation we did with our very basic computer nearly 20 years ago. And they simulated the system and they looked at charge and spin separation in an interaction system. So what is they find? So this is a quantum simulation. I mean, it could be done. I mean, if technology allows, in a system of called fermions, for example. But this is done with these superconducting resonators. So at time equals 0, they produce a wave packet, like it shows here in red and blue. And then they evolve in time, this quantum system. You see time is growing now towards the right. And they measure charge and spin densities, and they see that the charge is in blue and the spin is in red. They do not have a net momentum to the right like we had, but this wave packet evolves symmetrically to both left and right. As you see here, you see the charge both of them are open enough towards the left and right symmetrically. And then the charge, here you see a clear separation of density, so charge and spin. You see now the charge arrived to the borders while the spin is still centered in the middle. And then you also have a dispersion of the wave packet because, of course, the dispersion relation is not linear, but we have a curvature. So here they use 16 qubits, but with many, many other qubits for error correction. So this is using above 600 plus qubits to correct the errors in this system. How they simulate this, I mean, I don't know the details, but the main idea is behind this quantum circuits depicted here in this paper, where, for example, the J, they use J as a hop in, the same as the community of code atoms. So this is the hopping part, and here you see each one of these squares is a superconducting resonator. So it's a qubit, and they have special matrices that connect the different qubits. So simulating the interactions and the hoppings represented by these matrices that represent the quantum dynamics of these systems of resonators. So I can't go more into detail because I don't know the detail of this calculation, but this is the idea behind that calculation. So it was interesting to see how a very simple, calculation of charge and spin separation then was used by Google to reproduce and to simulate and to show that they can simulate a quantum system. Now, another example of charge and spin separation we did also several years ago is looking at this phenomenon in the transport through Aronoff bomb ring. So here we have two non-interacting leads, and in the middle we have an interacting one-dimensional system. And this ring is pierced by magnetic field, magnetic flux phi, which interacts with the phase of the electrons in the system. So then, by injecting an electron from the left and looking at the transmittance, so we inject an electron comes into the system at time 0, it evolves. So here it acquires a phase, and then we extract it at a later time from here to the right lead. And then looking at quantum interference between the different quantum states of this interacting system, we could see the fingerprints of charge and spin separation in this system, that we can see them here. Let me just briefly explain. This is the transmittance through the Aronoff bomb ring, the equilibrium transmittance at 0 temperature as a function of the magnetic flux, and this one is pi to the right. As you see, we have three different examples. The first one has two dips, one at 1/3 and a dip at pi. Now, this dip at pi is very easy to understand because this means this point here is a destructive interference of a non-interacting electron. So if you, let's see with a semi-classical interpretation, if you inject an electron inside 0, then one possible path is through the top, acquiring a phase phi over 2. The second possible path is through the bottom, acquiring a phase minus phi over 2. So when the flux difference is pi, then we have pi over 2 minus pi over 2 is there's a net flux of pi, and this is a destructive interference geometry. So there's zero transmittance of the electron. Now, what happens if when we inject the electron, then the charge and spin separate? The charge, as we know, usually goes faster than the spin. So in one path, the charge goes much faster and goes around many times until it recombines with its spin, and then we get a full electron to destroy. The second path is the other way around, so going counterclockwise, and the same happens. So then here now we have different commensurability or proportions depending on the ratio of the spin to charge velocities, and that gives us different values of the flux at which we get destructive interference. So here we have, for example, if the ratio of the velocities is 1/3, then we get a dip at 1/3, then we can have a ratio of 1/5, and we have different dips, and these dips are real fingerprints of charge and spin separation in the system. Of course, this is a theoretical model, and it has not been measured, but it's interesting to see, at least as a toy model, how to interpret the charge and spin separation. Well, now changing topics slightly. This is an example which I think is very, very nice. I mean, for explaining mainly to students the phenomenon of how strong interactions can produce fractionalization, in this case, of the magnetic dipoles. As we know, the magnetic dipoles cannot be separated, but if we have this spin ice system, for example, this is the crystal structure of this system, what it has is called spinite, which has dysprosium, titanium, oxygen. It's a collection, an ordered collection of tetrahedra. And then these, as you see, they all have, I mean, if you get one of them, they have two spins out. They have a spin on each vertex, two out and two in. So this is the A would be the ground state configuration of this system. Now, what happens if we split this spin, the spin in the middle, like in B, if we split the spin, then we produce a magnetic dipole, because the blue means we have three spins pointing out, and the red means three spins pointing in. And then now if we come to the solid and we continue flipping the spins of the vertices, we can see that we can separate the blue from the red, so the negative from the positive sections of the dipole, and this is how we can produce a string of dipoles separating in the whole system. And I think this is interesting. Another example of emergent phenomena, of course, is the emergence of superconductivity, mainly the high TC superconductivity, which was discovered already many years ago, and of which we do not have comprehensive theory or a microscopic theory which makes us really see, I mean, gives us the possibility of predicting new materials. I mean, this is still lacking in spite of all the decades that have passed since its discovery and the amount of people working on this. So we all know, I mean, this is how the critical temperature has evolved in time. And this is, for example, the crystal structure of one of the basic high TC superconductors, which is yttrium, barium, copper, oxygen, and which is mainly formed by copper oxygen planes separated by yttrium. So high TC today, is, as I said, is not understood. Even the normal state is complicated. However, the high TC catalyzed an enormous research in, again, I mean, it's strongly correlated systems, which of course existed before, but then now, I mean, it became a very hot topic, and brought many people to work in this system, and now made us think about what is the complex behavior of these systems. So this is one of my main concerns, is how to analyze or to study theoretically these systems, given that they are really, the complexity grows exponentially with system size, and how can we deal with this, with these systems numerically, for example. So as I said, complexity grows with system size, so there should be ways to optimize the information so we do not need to keep all the different quantum configurations of the system, and how can we optimize the system using quantum information. So this is a very basic example of what an exponential difficulty means in these systems. So for people for people that stem from computational science, these are exponentially hard systems, non-polynomial systems. How can we deal with these computationally? Let's think about the Heisenberg model. We have a collection, a one-dimensional collection of spins 1/2. This is the model, but independently of the model, the different quantum configurations we have here, as if we have we have a qubit, so 2 states per site. And so then for n sites, we have 2 to the n states. So this, the amount of quantum states or the amount of configuration grows exponentially with the system size. So there's no way to deal with this exactly if we want to go towards its thermodynamic limits. There's no way that we can use the computers to study this. So I mean, this a couple of decades ago, in 1992, 93, Steve White proposed what is called the density matrix formalization group, which I will very briefly describe now. But before going into that, I like this quotation to John Preskill, is studied several years ago, about the importance of using quantum information to optimize calculations. And he says, the most challenging and interesting problems in quantum dynamics involved understanding the behavior of strongly coupled many-body systems. So better ways of characterizing the features of many particle entanglements may lead to new and more effective methods for understanding the dynamical behavior of complex quantum systems. So it's very important, as John said several years ago, to characterize the excitations and to organize the information, like Bob Laughlin said in the beginning when I read you the quote. It's very important to organize the information in these quantum systems to be able to understand them. Otherwise, it's impossible because of its inherent complexity. So what happens? What is this density matrix normalization group? This was developed by Steve White in 1982 in Irvine in US. The quantum information interpretation came later, but this is the best way to interpret the development of the density matrix normalization group. It uses quantum information to keep the most relevant quantum state. So what it does is it begins with a small, this is one way of doing it. Now it's, with tensor networks and with matrix product states, the system, the method has evolved a lot, but this is the basic method of what we all know about, called tensor networks. And you might have read as one of the most reliable methods to calculate correlated systems. So in those days, then Steve proposed beginning with a very small system, let's say in the Heisenberg system with 4 or 6 sites. You can calculate the ground state of the system or the relevant excited state you want. Then you divide the system in 2. You calculate the density matrix in the red part of the system. The density matrix keeps the information of the state you're looking at, what is called a target state, whether the ground state or the excitation. When you diagonalize the density matrix, you get eigenvalues and eigenvectors. The eigenvalues give you the probability of finding the corresponding eigenvectors in the whole state of the system. So already the density matrix is giving us the information we need, because by keeping the eigenvectors with largest eigenvalue, this automatically gives us the optimum way of describing this quantum system. So that's what we do. We diagonalize the density matrix, we get rid and we discard all the eigenvalues, the eigenvectors that have very low eigenvalues, and we keep the ones with highest eigenvalue. And this is done iteratively while growing the system. Using this in correlated systems, including for quantum chemistry, including high energy physics, including nuclear physics, condensed matter theory, of course, and now many groups are using this to explain, to describe theoretically the system. So because why is it so it's so important to try to optimize the information, because we have to deal with systems like these monsters. This Hamiltonian. This is, for example, the 3-orbital Kanamori-Hubbard Hamiltonian. So this is to study interacting systems with several orbitals. In this case, 3 orbitals, or one can even need interacting Hamiltonians for more orbitals. But for example, if you want to study the pnictide or other interacting systems or high TC superconductors, you will usually need these Hamiltonians. And these Hamiltonians have hoppings between the fermions. This hopping, this has a chemical potential. We also have, we could have hoppings between different orbitals, and we have a very complex interaction term, this BI. And the local interactions include the Hubbard type local interaction U. We also have a J, which is a Hund J, usually, which is ferromagnetic, depending on the material we're looking at, but usually it's ferromagnetic. And we also have an interorbital Coulomb interaction U2. And these are different terms that come up in these models. So see, here you have the 3 orbital 1, 2, and 3 with different hoppings, and here we have the local interaction, and we also have interorbital interactions U2 and the ferromagnetic J here. This is a cartoon of what we study. Now, as this is very complex to study numerically. What we did is we studied the 2-orbital model, which could be useful for some of the materials. Let's see. It takes some time to change here. Let me just show you some examples of some calculations we did in a 2-orbital Kanamori-Hallberg model. So here we have 2 orbitals, orbital 1, orbital 2. Each one has their own bandwidth, because here we have we can say, for example, we have a hop in T1 and hop in T2. This orbital 2 could be much more localized. So the hop in T2 is much smaller than hop in T1. And we wanted to understand this system with our numerical method. So the first step was to study this model. I mean, here I'm plotting a one-dimensional, a chain, but the real systems have, of course, this is not a chain, but it could be a square lattice or even 3-dimensional lattice, okay? This is just a cartoon. What we did is we studied this system with DMST. The DMST is the dynamic mean field theory. I mean, this is one of the most important methods to study correlated systems that has to do with an approximation, which is, of course, it's a mean field approximation, but it's not a static mean field like the Weiss mean field, but it's taken dynamically. So one has to pinpoint a particular site of our 3-dimensional material. We pinpoint one site, and then we treat this in a dynamical mean field way. So the rest of the system is described as a medium, and then we come and go with iterative expressions of the DMST to calculate self-consistently the dynamics and the physics of this system. The main approximation is, of course, being a mean field theory, it's exact infinite dimensions, and it's taken as an approximation that the self-energy is local. So the self-energy does not depend on K. So this can be overcome by considering clusters. Instead of one single site impurity, one can consider a cluster. The cluster is already given us a little bit more structure to the self-energy, so it's not completely local. And this is improved a lot the efficiency of the DMST. Now, I mean, here, of course, this method was developed a couple of decades ago, and here is there's a reference to the people who developed that. The DMST, I just don't want to go into detail, but it's iterative. So all these different steps are part of the iteration procedure. You start with a zero self-energy, then you want to create the self-energy because we're going into the interacting system. Once you start with a zero self-energy, we calculate the Green's function. And then the Green's function, this is numerically, it gives us a hybridization. Then we have to fit the hybridization. Now we have to fit it numerically with an effective Hamiltonian given by this. So I don't want to go into detail. This is only for people who are more or less in the topic. Once we have the hybridization, we can obtain the Green's function of impurity, and this is where we use the density matrix normalization group. I mean, what we did is, given our experience in the DMRG, we used this as the impurity solver of this monster method. Once we get this Green's function, then we can rewrite the self-energy, and we go and we start again with a different iterative procedure. Remember that this impurity is an effective impurity. It's not a model. We're not looking at impurities. We're looking at a 3-dimensional model, but we call it the effective impurity is the site we have pinpointed to proceed with this mean field theory. There are many impurity solvers. Many different numerical methods that have been used. So here you see several of them using like exact diagonalization, Monte Carlo, non-crossing, or a numerical organization group. We use a DMRG that has also been developed by a German group. So what is this impurity solver? At a certain point of the DMST, we have this effective impurity, which can be a cluster, the impurity alone has the interaction. The impurity is embedded in a non-interacting system, and so the impurity plus the non-interacting system forms the Hamiltonian we have to solve and for which we have to calculate the Green's function. So how to solve that? This is the bottleneck of the DMST procedure, and this is where we use the DMRG, which turns out to be very efficient and has many advantages over most of all the other methods I showed you, since we can directly calculate the Green's function on the real axis directly. We do not need to calculate it on the Matsubara frequency, so I omega. We do not have to do that like it's done with quantum Monte Carlo, for example. This is a drawback of quantum Monte Carlo, because if you converge on the I omega axis to calculate the Green's function, then if you want to calculate, for example, densities of states or real frequency response functions, you have to use ill-posed extrapolation procedures like maximum entropy or whatever, and to take the information of the Green's function on the I omega axis to the real axis, and this gives you real, sometimes very misleading results, and it gives you too much of an error. So this is so important to have impurity solvers which converge directly on the real frequency axis. However, just let me, to say something positive about the quantum Monte Carlo, for example, continuous CTQMC, continuous time quantum Monte Carlo, the positive thing of that method is that it can be used to calculate finite temperature, whereas with these methods, one cannot, still not include finite temperature in the system. Another positive outcome is that one can calculate all frequency scales. So contrary to what happens with NRG, numerical organization group, a la Wilson, which only concentrate on very small omega scales. Now, using symmetries, one can really go to a little bit higher omegas, but NRG is usually focused on very small energy scales, whereas DMRG allows us to calculate for all omega scales. We can use arbitrary interactions, so this is to improve the iterative IPT methods, etc. We don't have any sign problem like in quantum Monte Carlo. We can use large bars, much better than exact annualization methods, for example. We can also use several orbitals. This is for clusters, DMSTs, and we can also use several sites to calculate a K dependence of the self-energy. Well, after I told you about all the good things of the DMRG, let me show you some results. But just to frighten you a little bit more, I want to show you what a complex impurity looks like in this DMST calculation. So this is, for example, the top one is what the square is the interacting impurity, and the circles are non-interacting sites of the non-interacting bands. So here we have a star geometry. A star geometry represented, in a flat way. But if you open this up, it looks like a star. And this is what we have to calculate if we have a one single band or single site impurity. What if we have two? If we want to look at the cluster DMST, if we have two single band impurities, or we have one single site with two orbitals, which is completely equivalent, each orbital of this complex impurity of two squares has, here we have a U, here we have the U, we have the hybridization, the J, whatever, all the interactions are here, and we have the non-interacting band, and the hybridization is included like this. And then if we go to larger systems, if we have four orbitals or four sites, for example, if we want to look at the Hallberg model, we can look at the four different sites and include longer term interactions, etc. And this is what it looks like, and this is what we have to calculate with the DMRG. And well, it can be done, and we need many sweeps of the DMRG, and it gets complicated, but in principle it's feasible. So now, just to finish, I want to show you some results very briefly, because my time is flying. Just very briefly, we looked at it, as I told you, the two orbital Hallberg model within the DMST. So our single site this is two orbitals. So orbital 1, orbital 2, we want to look at the orbital selective Mott cases. So where we have, for example, one of the bands is a metal and the other band is an insulator. For example, T2 is much smaller than T1. We found interesting results because with this method to calculate the dynamics using DMRG as impurity solver or the DMST, sorry for all the acronyms, we're able to really get the detail of the structure of densities of states that had not been seen in previous calculations using quantum Monte Carlo, for example, or even NRG. So we're happy to find new structure in models that are really paradigmatic for these materials. So what do we see? For example, if the U, a single site U is large, U equals 4, of course, both bands, the black is orbital 2 and the red is orbital 1. Both bands are insulating, so here's 0 is a Fermi energy. We have no density of states. We have the lower and upper Hallberg bands. This is a well-known Mott insulator for both orbitals. If we go to the other extreme, if the U is not too large, U is smaller than the critical U, we find the lower Hallberg band, the upper Hallberg band, and in the middle, for omega equals 0, we find a finite density of states for both bands, the red, orbital 1, and orbital 2, the black. We also find some structure, some in-gap structure here, which I'll tell you now about. The interesting thing was that when we put an intermediate value of U, you see the black orbital 2, the black density of states is 0 at the Fermi energy, so we have an insulator, whereas the orbital 1 density of state is finite, so we have a metal. So orbital 1 is a metal and orbital 2 is an insulator. We're in the presence of the orbital selective Mott because it's a Mott in orbital 2. But as you see here, we find very conspicuous peaks in band 2, and these peaks, if you add them up, they exactly add up to the weight of the central peak here. And it took us to think about the origin because these peaks hadn't been seen before, and we could identify them as hole-on-doublon quasi-particles in the system, as depicted here in the cartoon. So a hole on one orbital and a doublon on the other orbital, and that moves as a single entity in this material. When both bands are metallic, like in this top figure, we can see the quasi-particle peaks in both bands. What does this mean? That as long as we have holes in one band, in the metallic band, that hole couples to a doubly occupied site on band 2, and this is seen only by the density of states in band 2. Because if we look at the density of states in band 1, we would never have holes in the band 2 to couple to, because since band 2 is an insulator. This has a very interesting consequence, and it's the question is whether we can have an orbital selective Mott transition when we have the symmetric case where local U is equal to the interband U prime. And well, I mean, this is the long-standing controversy between different groups. And just to show you very briefly, even if we have, this is the quasi-particle peak Z as a function of the interaction. If you look at this red curve here, the quasi-particle peak, even if we have a very, even if the hopping in band 2 is 50 times smaller than the hopping in band 1, so we have a very narrow band 2, the band 2 still has a finite density of states at the Fermi energy, which is exactly the same as the density of states or the metallic orbital. And this is due to the fact that both the local U and the interorbital Coulomb interactions are the same. So the presence of holes in the metal is forcing a metallic state in the very narrow band 2, although the metallic state on band 2 is a very special metal we still don't understand well because it's not a normal Condor peak on the orbital 2, and this still has to be studied. So the two last figures I wanted to show you is, for example, we have studied also this model but for the doped system. And in the doped system here we find, this is a very basic figure, but if you look at the density of states for different values of the interorbital Coulomb interaction U2, we crank up U2. Let's see, U2 equal to 0, so we have two independent Hubbard chains. Hubbard bands, because it's two-dimensional Hubbard bands. So it's a doped system. So here we have the lower Hallberg band is partially filled, and towards 3, U omega equal to between 3 and 4, we have the upper Hallberg band. If we crank up the interorbital coulometric reaction U, we find that there is a weight transfer that is that comes out, that stems out from the higher upper Hallberg band, and it goes down to lower energies, as you see here. And this is what we identified as the Holon-Dublin band. So if you look at the middle curve here, we see a very interesting Holon-Dublin kind of band, a new structure between the lower and upper Hallberg bands, which has mostly weight in the Holon-Dublin excitations, although it's not purely Holon-Dublin bands. So this we found interesting. We can also study as a function of the chemical potential. I mean, how these Holon-Dublin bands arise. I will not go into details with that. What happens with J, the Hund J, the ferromagnetic J between the orbitals, also split these bands, as you see here with these purple triangles or even the green ones. So the J is also splitting these new bands. And this is an analysis of the composition of the different bands for the doped case. Here we identify this Holon-Dublin band as mainly composed by Holon and Dublins, and then the lower Hallberg band also splits into different components. The spectral density, I mean, this is how the Holon-Dublin band, is this red, how it has weight mainly at k equal to 0, but I mean, we still have to study the dynamics and the dispersion of this band. Well, I think my time is already due, and just to tell you, I wanted to convey to you and mainly to students that with this beautiful view of the Fitzroy in Patagonia, that the correlated quantum matter is still one of the most interesting and complex and challenging areas in science. And we're just in the beginning, and we have a long way ahead. So I want to thank all my collaborators, which are listed here, and also my students. Just to show you here, there are so very few women working in this area here. I have 3 women collaborators, plus my students, among over 30 main collaborators. And I hope the situation can change in the future with many more women getting involved in this very exciting area. So, well, thank you very much again. And I leave you with this view of the Fitzroy. And I'm, of course, open to questions. Thank you for your attention.
Thank you, Karen. Thank you very much for the very interesting talk. So I think now we can move to the questions. If there are any questions, you can use the chat or raise your hand. So I can start with I have 2 questions. The first one, I think in the your third slide, or you show some molecules, and then for some number it becomes this crystalline. You have some structure.
Yeah.
So here this. If you have, for example, one less molecule, and then you put a molecule, how does it go through this phase? It's like by bubbles, and it expands, and how does it?
Yeah, I don't know exactly in this paper, because in this paper it doesn't go into that detail. It just shows you they add, several. It's not one by one, because it's the phase, this transition or the emergence of crystal order emerges after a certain amount of water molecules, like I was telling you. But I don't know how individually how this propagates. This is a very interesting question. I don't know. I don't know the answer to, but there are people studying how, this is a phase, like a phase transition. You have part of the molecule is in a certain order and part of it is not, and how this phase grows. It's like you have to study domain wall growth, etc. And if they have universal laws, universal exponents, it's interesting, but I can't answer precisely your question, Diego. But it's a very interesting topic, of course.
Okay, Thank you. The other one, it's just, what is the sign problem that you mentioned in quantum Monte Carlo? It's just, I don't know about it.
Yeah, the quantum Monte Carlo has inherently a sign problem always when you're in any quantum Monte Carlo, except for a few that tries to overcome this problem. The sign problem is that when you exchange two fermions, two electrons in the, for example, if you look at the path integral or the lines of the evolution of the electrons, when they cross each other, there's no fermionic sign taken into account in the quantum Monte Carlo. And this, I mean, this that has, of course, has to be taken into account because you have two fermions, and when you exchange them, you have a minus sign. This is taken into account automatically with other like exact diagonalizations or with quantum problems, but not in the quantum Monte Carlo. So one has to be very careful with this sign problem, and it can give you erroneous results.
Okay. Okay, thank you. So there is question from Angela. Maybe Angela can, if you want to ask a question, I can read the chat, but if you want to unmute yourself and ask the question. Angela? I don't know if. Okay.
Hi, can you hear me? Yeah.
Yeah. We can
hear. Hi, Angela.
You can ask. Please
great
go on.
talk. Yeah. Very nice, the spin charge separation explanation. Good, I will use for some students in the future. Really nice. Yeah. So could you comment a bit about some applications of two of the Hallberg models that you discussed, this Karamori-Hallberg and the two orbital Hallberg models?
Yes. Well, for example, if you look at the pnictides, or for example, if you look at the ferromagnetic high ITC superconductors, then it's important to consider several orbitals in these systems, because you have the orbitals of the transition metal oxides, and you have to look, the basic model for these materials is the Kanamori-Hubbard model. It's a very nice review by Antoine Georges and by other people where you can find, if you write an email, I can send you the review. But I mean, most of the correlated high TC materials have to include several bands, and this way of doing, because you have more localized bands and more itinerant bands, and you have to include models like the Kanamori-Hubbard model. I mean, it's really three bands, because you have the T2G orbitals separated from the EG orbitals, and then, I mean, it's enough to consider only three bands sometimes. And then the two, if you want to go back down to two bands, if you want to explain, for example, nickelate, you can use for some compounds the two orbital Kanamori-Hubbard model. And in some cases, you have the ferromagnetic J, and in others not. I mean, I'm very general in my reply because, I mean, depends. These are one of the most generic models to study these systems, these materials. So that's why it's so important to be able to solve them, because this is the way we try to explain some of the interesting experiments.
Okay, thank you.
Okay, so we have a question from Peter. Peter, if you want to. Peter. I don't know if he's. I can read the chat. Okay, there is a question by Peter. Okay, I can read. Why the carriers of fundamental forces are vector bosons, except the Higgs that is a scalar? Shouldn't the elementary boson of a vector force be a vector boson as well? I don't know if there is any relation.
Well, I think it's very, I mean, this is something that it exceeds my area of expertise. Because it has to do with the fundamental forces. I'm sorry, Peter, I can't answer this in detail. I think, for example, the graviton is not a vector. It has spin 2, so that should be a tensor. But the question is, shouldn't the elementary boson of a vector force be a vector boson also? Yeah. Well, I don't know. This maybe you should ask. I'm sure there are people at the IIP who can answer this, because the people working in the fundamental forces. My message is that we do not need to know this detail to explain the physics of correlated materials. So this is not something I can answer.
Okay, so maybe you can move to Bhaskar if you want to. He has a comment, and maybe Misha has a question. Misha Portugal, if you want to unmute yourself.
Maybe
yeah.
Bhaskar can.
Bhaskar,
because it has to do with the number of molecules that I was asking in the beginning.
Yes. So Bhaskar,
yeah.
Please go on.
If there is no question from Bhaskaran, then Misha will ask. Yes, is it okay?
Okay.
No,
can you
Okay.
Can you please show again a slide with these rings? The rings with tight binding model and leads and things. I don't remember which one it was exactly.
Well, you want the result, or you want the set? This is the setup.
No, just yes, this one. Yeah, okay. No, back.
Okay.
The previous one with the sketch itself. One before this one. Yeah.
Yeah, this one.
Thank you very much. What happens, for example, if you have two T's, like similar to SSH model or something, not just a simple one T parameter, but kind of two T1 and T2, two particle cells or whatever you would call it. Because then you will have a gap and things like that, rather than simple cosine. Does it make some difference?
Well,
or did anyone do
it? It depends, of course, on the model. You're proposing a model. I mean, here in this second in B.
Yeah, in the second, in fact, you have two particles. So there is it is in some sense in the ring inside. It is an SSH. That was partially motivated.
Yes.
But what happens if you also have because you have two reflection symmetries, yes, in the straight line, horizontal line, and in vertical. What happens if the sides, if there is one of that mirror symmetries is missing?
Well, for example, if you do not have the same amount of spins at the top than at the bottom, of course, because you have, if you look at a semi-classical interpretation, then you have a different path length at the top than in the bottom.
Where I'm going was that maybe you can then not pierce with the flux. Maybe you can have, an effective magnetic field just due to the loss of symmetry, because it is, if the ring is still if you try to keep quantum coherence and to have a physically large flux piercing something which is that small is difficult. So I was thinking that maybe I can substitute flux by asymmetry in my arms.
Yes, well, this would be interesting, because what you say is really true. I mean, this is in a real system. If this is a molecule, you cannot pierce it with a magnetic flux. You need several Tesla, and this would be then it would change the spin because it would couple to the magnetic degrees of freedom as well, not only the flux. But if you look at, for example, at a different configuration, or even the charge Aronoff configuration, where you put a gradient, a field gradient here, an electromagnetic gradient, then you could also see something like you're suggesting. You can also create it by let's see, if we do not have a magnetic flux here, we also studied some molecules, for example, and depending on where you put the right leads, if you put it up here or you put it 90 degrees or wherever, you can have different conditions of destructive interference. And this is another way of looking at charge and spin separation. Of course, yes, you're right.
And I can think also about a twist. If the upper ring is twisted with respect to the lower one, then I already have pseudo vector, which is effectively like a magnetic field. Yeah, so I see. Okay, so it's, yeah, I will read this stuff maybe and.
Well, if you have any questions, please, with pleasure. This is something we did several years ago, but it's still interesting. I think, at least from the fundamental point of view of trying to see different ways of measuring charge and spin separation, because up to now they're all indirect, like I mentioned. So anything you can come up with, I think, would be interesting.
Okay, thank you very much.
You're welcome.
Okay, I think now Dimitri, please.
Thank you very much for the interesting talk, Karen. So I have a question about the same, about the von Harmonic rings. So these fractions in the transmission coefficient that you showed us. So my naive question, could you remind where these fractions come from, and what happens if you, for example, change the edges of this ring? So if it in a non-symmetric way, so how the fractions would change?
Okay. So for example, imagine the spin to charge velocity is 1/3. Okay. So then when you put an electron into the ring, imagine the charge this is semi-classical, okay? The charge has to go around 1.5 times, and the spin only did half, okay? So that's a recombination condition. The charge goes 1.5, and in that moment it recombines with the spin, and one can have transmittance, because you inject a whole electron and you destroy a whole electron with its charge plus spin. So as the charge goes around 1.5 times through the clockwise path, the other charge goes around -1.5 times in the counterclockwise path, and it recombines with its spin. So if you add up that 1.5 plus 1.5 is 3 times collecting flux, and so the effective flux has to be 1/3 then to be able to meet pi, okay? And so then the minimum for a destructive interference occurs at 1/3 of pi, as is shown here. And this is a numerical calculation where really we find destructive interference at 1/3. And the same if 5 means a fraction of 1/5 for charge to spin velocities, etc. Now, is that clear, Dimitri?
Yes. Yes. Thank you.
Okay, so then the second part of your question was, if now we have a different configuration of the leads and drain leads, then you have different path lengths, and one should calculate in a similar way what the conditions should be, but there you have a different path length if you want to look at it semi-classically. But if you want to look at it quantically, you can. I forgot to say, and it's important, that this ring is very lightly connected. With the leads. This T prime here between the hybridization between the ring and the leads is very low. T prime is very small, because so then you have the ring has maintained its own quantum states, and these quantum states are very little hybridized with the lead. Now, so then you can calculate the states of the ring, and then look at the different quantum states and look at the Green's functions to calculate the transmittance through this ring and look at the conditions. It would be interesting to see, but you're going to write a similar thing.
So there's no quantization in this case, or will there? So in principle, if you make them any any length, then probably you would expect continuum. You can manage any fraction. Okay.
Yeah, exactly. Yeah, it will be interesting to see. It hasn't been done yet.
Okay. So if I may, there's a question on YouTube, so I will read it for you from Luan Martins. So he asked about impurity solver with DMRG. And I think his question is about what do you think about using imaginary time evolution, TEBD, and projective entangled pair states in this case? And if there's equivalent applications for 2D systems.
Yeah, I mean, so this is, let's see, this is a proposal for an impurity solver by doing imaginary time evolution and then projecting it. This is a way of solving the dynamics and of calculating the Green's functions. But there one has to see how to reach all the different omega scales. Because if you want to get to very small omegas, you have to let it evolve for very large time scales. And sometimes then the DMRG in this imaginary time evolution constantly acquires an error, which is you collect an error, and the larger the time, the more error you are producing. So then one has to be careful of when to stop with the time evolution. If you have a finite system, you also have a discretization of the energy levels, and you have to be careful with, you have to extrapolate. So it has its drawbacks, but I think it's worthwhile pursuing to see if it can also improve the impurity solver. I think it's interesting, but these are my caveats I can tell you about.
Okay, thank you very much for the answers, and on behalf of Luan Martinez also.
I think now, Fabio, you have.
Thank you, Thiago. It's me. Karen, thank you for this excellent talk. It's just a comment. I would like to hear your comments about the spin chart separations, 2 dimensions, because as you know, you showed many good results in 1D, and there are several analytical, numerical, and experimental results which do agree with the spin chart separation in 1 dimension. But in 2, what is your comment about?
Yeah, in 2D it's more marginal because, for example, let me show you. I mean, the results we had with this ladder system with the Bomaranov transmissions. Here we had different results. I mean, this is a way of trying to go towards 2D by adding a perpendicular hopping. Okay, if a perpendicular hopping is very, very strong, of course we can go back to a 1-dimensional system where we have the bonding and anti-bonding combinations of each rung, and then we combine them very lightly with a parallel hopping, and then we go back to a 1D system. Now, when the parallel and perpendicular hoppings are comparable, then we had a mess of dips, and the spectrum, of course, becomes much more complicated, and it was impossible to distinguish these fingerprints of the minima in this situation. So only for extreme cases when you can project them to 1D, we could find clearly the charge and spin separation. So we tried to do exact diagonalization in 2D also many years ago, and we could find some signature of charge and spin separation for the Hallberg model, and it was not at all clear. So I know there have been many other attempts now, but my basic understanding on this is that in 2 dimensions, depending on the model, I mean, you could have charge and spin separation, but for the normal Hallberg model, or TJ, let's say, it's very difficult. I mean, you have a less clear separation between charge and spin. Let me even clarify. In this, even in 1 dimension, if the U is not too large, if you have intermediate values of U, the charge and spin separation is not complete either, because you have you do not have separate excitations of charge and spin completely separate, which you do get when in the limit of infinite U. So you also have intermediate regimes for one dimension, and you could find like a string of charge and spin, but for intermediate values of U, they're never completely independent.
Right. Thank you for your answer.
You're welcome.
Okay. Sorry, Bhaskaran, you mentioned that you had a comment, but if you want to make the comment, maybe the last comment. Yeah, it's very, I cannot hear you well, but I don't know if other people can.
Yes?
Bhaskaran? Yes, I can. Yeah, it's very, the volume is very low, but let me try.
Can you hear me now?
Yeah, there are some big noise.
Okay, I'm sorry, maybe I think there is some problem with my computer.
Okay, so sorry, maybe you can make your comment and then we end there. Are you, if you want to make your comment, we can hear you. There is some noise, but
okay, so I wanted to make a comment about the number of particles at which phase transition occurs. There is a beautiful experiment with liquid helium-4 droplets done at Emergent. They find that when the number of helium-4 atoms exceeds 60, there is superfluidity in the helium droplet. Very sharp change. Which we take spectroscopically. And also, when the drop becomes slightly bigger, they could see even quantized vortices. So it's a beautiful quantum system. The superfluid order manifests experimentally in a very neat way. And the critical number is like 60. And
sorry, Bhaskar, I don't know if all the other people can hear you. I lost the.
Okay.
I'm very sorry. I think it's hard. I was hearing in the beginning, but now I lost your comment.
No problem.
So thank you. So maybe we can. Yeah. So thank you very much, Karen, again for the great talk and thanking everybody for the participation and hope to see you all in the next seminars. Okay.
Thank you, Thiago. Thank you, everybody, for coming and keep up this very excellent seminar series. And so I thank you all for coming.
Thank you very much, Karen. Thank you.
Bye-bye from Bariloche. Goodbye, everybody. Bye. Thank you.